All right, ladies and gentlemen, this is Mark Anderson for Keller Community College, and this is our fourth video, or the fourth page of the review for the Unit 3 test. And we're going to look at another hypothesis test here. We are going to look at two sets of data comparing the weights of two vacuum cleaners. We have brand X and their various weights, and brand Y. As you see, there are many more of brand Y and their various weights, and we're going to see if there's enough evidence to claim that both machines really weigh the same, or is one brand much lower than the other. Well, by saying that, we have our since we're comparing two different groups, the null hypothesis is going to say that group 1 is the same as group 2, and there's no significant difference between the two of them with an alpha of 5%, which means that we have a 95% of not making a type 1 error. And then the alternative is going to say, no. See, we're just trying to claim that both the machines are the same, and I'm telling you that these two groups of machines, they're not the same. So this is going to be a two-tailed test, and that's important when we talk about all the different things we get to do with our critical value. And let's actually do the critical value right now. The critical value is going to be, since we have 1, 2, 3, 4, 5, 6 items here, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 items here. When we look at these, we'll notice that both of them are under 30. And if both of them are under 30, this is a slam dunk for a t distribution. So we're going to use our t-chart. Now, our t-chart is based on degrees of freedom. And it's important to use the degrees of freedom from the smaller of the two sample sets, because that will give us a higher critical value, which also means that we will have to work harder to prove that these groups are statistically significantly different from each other. Well, the degrees of freedom is n-1, so we're choosing the smaller of the two sample sizes, so we're going to go with 6 minus 1, or the degrees of freedom is equal to 5. So we go to our t-chart, and look on 5 on the left-hand side, and then we're going to move over to the right where it says two-tail and an alpha of 5%. And if we do that right, we get a critical value of plus or minus 2.571. Now, your table does not give you the plus and minus. It just gives you the positive value, but that positive value would only be for right-tail tests. Two-tail tests would be plus and minus, and a left-tail test would be minus. So keep in mind that you have to kind of, even though the t-chart is much easier to use than the z-chart, because the z-chart has you thinking about how to convert your percentages into a proper critical value, but you do have to remember your positive and negative signs when dealing with t-value or t-charts. Alright, so what I'm going to do is I'm going to rewrite, since I want to, it looks like my test here, I'm going to kind of squeeze it in here at the top. I'm going to rewrite part B over here on the corner of this screen so you can see what we did before. Our critical value is equal to plus or minus 2.571. And that was part B. Part C, or our third part, is to run the test value. And the test value is going to be our x sub 1 minus x sub 2, subtracting our mu sub 1 minus mu sub 2, which is always 0 in these cases. So, because if we have the difference of the population minus the difference of the population, that would be 0. And then down below we have the standard deviation, and in this case it's going to be lowercase s because we have under 30 pieces of data. The first standard deviation squared divided by the sample size of the first group plus the second standard deviation squared divided by the sample size of the second group. Now, it is important to see that all of the data was given. So what you would need to do is you would need to go to your graphing calculator and type all of the brand X weights into list 1. Run your one variable stats like we did in chapters 1 and 2, or units 1 and 2 I should say, and that would give you an X bar, or an average of those weights of those vacuum cleaners is 10.7. And the standard deviation, denoted by a capital letter S on the calculator, is going to be 4.8. And I'm rounding to 1 decimal because everything else is whole numbers. Now if I enter into list 2 or I retype list 1 with all the brand Y weights, I get an average of 13.3. So it looks like right now the brand Y weights are much heavier. And if I then do my standard deviation, you'll notice that the brand Y weights are actually much closer together. They don't vary as much. But this still gives me a little chance to think like, hey, this 10.7 and 13.3 are 3 away, but their standard deviations, when added and subtracted from these numbers, do have overlap. So I might have a situation where they overlap enough so they won't be statistically significant. But let's find out. Let's plug in our x sub 1, and I'm just going to call this x sub 2 here, just because that was for my y weights. And this is going to be my standard deviation for the first group and the second group. So I'm going to plug it into this equation here. So let's first of all subtract these. Now because this is a two-tailed test, I don't have to worry about the order. If I had flipped the order, I would just appear on the right side versus the left side. But that's going to be okay because this is a two-tailed test. So in right tail and left tail tests with two variables, you have to be a little bit more careful. Now down below, we're going to have the square root. And the square root is going to have the standard deviation of the first group, so 4.8 quantity squared divided by the sample size plus 2.5 squared divided by 17. And then I'm going to compute all this, and a lot of you don't even write the -0 anymore, but this numerator then divided by the denominator is going to give me an approximate answer of -1.27. To draw my picture here, this is going to be 0 in the middle. This is a two-tailed test, so I have two tails on both sides, and this is going to be a -2.571, and this is a positive 2.571. The -1.27 is going to be here, inside of the non-critical region. And since this is not inside the critical region, we do not reject the null hypothesis. These two vacuum cleaners are too close together in terms of their weights, including the standard deviations and the error that I've adjusted for my 95% confidence interval, or alpha 5%, that I am going to say that since -2.571 is less than -1.27, which I could have flipped this around and said -1.27 is greater than -2 and 571 thousandths, we will not reject the null hypothesis. All right, well, thank you for watching.